Hello friends, today we are going to discuss solid state chemistry. Solid state chemistry is an important chapter in 12th class chemistry, and this episode is brought to you by www.chemistrynotesinfo.com. Matters which possesses rigidity having definite shape and definite volume is called solid. Types of solid: crystalline solid and amorphous solids. Metals, non-metals are example of crystalline solids, where rubber, glass, plastic are example of amorphous solids. Difference and comparison between characteristics of solids. Crystalline solid. Crystalline solids contain regular arrangement having short range as well as long range order. They have definite geometric shape, sharp melting point, they have definite heat fusion, they undergo clean cleavage, and they are true solids. Now we are going to discuss amorphous solids. Amorphous solids contain irregular arrangement having short range order only, irregular shape, melting over range of temperature. They do not have definite heat of fusion. They undergo an irregular cut. They are pseudo solids or supercooled solids. Classification of crystalline solids. Crystalline solids are classified as ionic solid, molecular solid, covalent of network solid, and metallic solids. First is ionic solid. In these crystalline solids, constituent particles are positive or negative ion held together by Coulombic or electrostatic force of attraction. Example: NaCl, MgO. Now we are going to discuss molecular solids. There are three types of molecular solids, that is non-polar molecular solid, polar molecular solid, hydrogen bonded molecular solids. Non-polar molecular solids. In these, the constituent particles are atoms of noble gas, and or non-polar molecules are held by London dispersion forces. Example: argon, H2 means hydrogen. Polar molecular solids. In these solids, constituent particles are held together by dipole-dipole force of attraction. Example: HCl, SO2. Third is hydrogen bonded molecular solids. In this type of molecular solids, constituent particles are molecules containing hydrogen linked to fluorine, oxygen, and nitrogen, held by hydrogen bonding. Example: H2O, NH3, H2O in the form of solid, that is ice, and NH3. Covalent or network solids. Covalent or network solids are the solids which have the constituent particles or atoms held together by covalent bonds. So its name suggests its definition, means covalent or network solids are the solids whose constituent particles are atoms held together by covalent bonds. Example: carbon in the form of diamond, SiO2 that is in the form of quartz. Metallic solids. Constituent particles are positive ions in a sea of mobile electrons held together by metallic bonds. Example: all metals and alloys. Now we are going to discuss crystal lattice. So crystal lattice is a regular arrangement of constituent particles in 3D is called crystal lattice or spatial lattice. I repeat, regular arrangement of constituent particles in 3D is called crystal lattice or space lattice. Now we are going to discuss unit cell. The smallest three-dimensional portion of a complete space lattice which when repeated over and again in different direction produces the complete space lattice is called unit cell. Now we are going to discuss Bravais lattice. The 14 lattices corresponding to 7 crystal systems are known as Bravais lattice. Coordination number. The number of spheres touching to a particular sphere is called coordination number. So, number of atoms per unit cell is equal to number of atoms in simple cubic lattice. 8 atoms are at corner. It is the example of simple cubic lattice, that is 8 into 1 divided by 8 is equal to 1. Number of atoms in BCC. 8 atoms are at corner and 1 in the body, that is BCC structure. B 8 into 1 divided by 8 plus 1, that is equal to 2. So its coordination number is 2, or number of atoms per unit cell is 2. Number of atoms in FCC. 8 atoms are at corner and 6 atoms are at face, 1 on each face, that is the structure of FCC. So it is 8 into 1 divided by 8 plus 6 into 1 divided by 2, that is equal to 4. Dear friends, you can see the images of the structure, that is FCC, BCC, simple cubic lattice, by visiting our website www.chemistrynotesinfo.com. There you get a section called 12th class. Click on that section 12th class and there is a first chapter, and click on that chapter to open the notes of this chapter. You also find the link of this chapter in the description of this podcast. Now we are going to discuss closed packing in crystals. Closed packing in one dimension. Spheres are touching each other in a row. In this arrangement, coordination number is 2. So, second is closed packing in two-dimensional. It is done by two ways: square closed packing or hexagonal closed packing. First is square closed packing. In this arrangement, spheres of second row are exactly above the sphere of first row. And hexagonal closed packing. In this arrangement, the sphere of second row may be placed in the depression of the first row. Closed packing in 3 dimension. 3-dimensional closed packing from 2-dimensional closed packed layer. Starting from the square closed packed layer, the second layer and all further layers will be built up such that they are horizontally as well as vertically aligned with each other. 3-dimensional packing from 2-dimensional hexagonal closed packing. When spheres are arranged in hexagonal closed packing in second, two types of voids, that A and B, are formed. A and B voids are triangular when second layer is placed over the void of the first layer. Only one void is fulfilled in hexagonal closed packing, and these layers form two voids: C triangular, D octahedral. Dear friends, I know it is difficult to understand the definitions of these types of closed packing by listening only. So please do visit our website to see its pictorial, so you can see or you can understand easily by seeing the pictures of these closed packings. To visit our website, type chemistry notes info in Google and you find a link of our website www.chemistrynotesinfo.com. From there you can visit this chapter to see the pictures. Next is packing efficiency. The percentage of the total space filled by the particles is called packing efficiency. I repeat, the percentage of total space filled by the particles is called packing efficiency. Next is packing fraction. The fraction of the total space filled is called packing fraction. Calculation of space occupied. First is in a simple cubic unit cell. Suppose radius of a sphere is r. Edge length of unit cell is a. A sphere are touching each other. So a is equal to 2r. Number of sphere per unit cell is equal to 8 into 1 divided by 8 is equal to 1. So volume of sphere is equal to 4 by 3 pi r cube. So volume of cube is equal to a cube, that is equal to 2r cube, that is equal to 8r cube. So packing fraction is equal to 4 pi r cube divided by 3 into 8r cube is equal to 0.524. So percentage occupied is equal to 52.4%. And in similar way, second is in face-centered cubic structure, closed packing, cubic closed packing. Spheres of face center touching the sphere of the corner, then AC is equal to 4r. In similar way, AC is equal to root AB square plus BC square is equal to root A square plus A square is equal to root 2A. So root 2A is equal to 4r or 4r divided by root 2. So volume of cubic unit cell is equal to A cube is equal to 4r by root 2 s to the power 3 is equal to 32 by root 2 r cube. Number of spheres in unit cell is equal to 4. So volume of 4 spheres is equal to 4 into 4 pi r cube divided by 3 is equal to 16 pi r cube divided by 3. Packing fraction is equal to 16 pi r cube into root 2 divided by 3 into 32 r cube is equal to 0.74. Dear friends, if you feel any difficulty in understanding these numericals or these examples, please do visit our website to see, to understand easily. So percentage occupied in cubic closed packing is equal to 74%. In body centered cubic structure, sphere at body center touching the sphere of the corner. So body diagonal AD is equal to 4r. Further face diagonal is equal to AC is equal to root AB square plus BC square is equal to root A square plus A square is equal to root 2A, and body diagonal AD is equal to root AC square plus CD square is equal to root 2A square plus A square is equal to root 3A. Therefore, root 3A is equal to 4r, or A is equal to 4r divided by root 3. So volume of unit cell A cube is equal to 4r by root 3 cube is equal to 64 divided by 3 root 3 r cube. So number of sphere per unit cell is equal to 8 into 1 divided by 8 plus 1 is equal to 2. So volume of 2 sphere is equal to 2 into 4 by 3 pi r cube is equal to 8 pi r cube divided by 3. So packing fraction is equal to 8 pi r cube into 3 root 3 divided by 3 into 64 r³ is equal to 0.68. So percentage occupied is equal to 68%. So radius r of the octahedral void is equal to 0.414 r, and radius r of the tetrahedral void is equal to 0.225 r. In CCP and HCC, if there are n sphere in the packing, number of octahedral voids is equal to n, number of tetrahedral voids is equal to 2n. Now we are going to discuss imperfection and defects in solid types of defects. Stoichiometric defects, non-stoichiometric defects, impurity defects. First we are going to discuss stoichiometric defects. In these defects, the ratio of anions and cations remains same as the stoichiometry of the substance not change. These are also classified as vacancy defects. Vacancy defects are the defects which arise when some sides of the crystal lattice are vacant. It decreases density. Second is interstitial defect. When some constituent particles present in the interstitial side increase the density of the crystal. I repeat, interstitial defect. When some constituent particles present in the interstitial side, it increases the density of the crystal. Third is Stokes defects. If in an anionic crystal, positive or negative ions missing their lattice sides so that electric neutrality is maintained. Example, NaCl, KCl, CsCl, AgBr. Frankel defect. If an ion missing their lattice side, causing vacancy or hole there, and comes in the interstitial side, so maintain electric neutrality or stoichiometry of the crystal is called Frankel defect. Example, ZnS, AgCl, AgBr, AgI. Non-stoichiometric defects. In this defect, ratio of cation and anion became different from the original ratio. It is of two types, metal excess or metal deficiency. First is metal excess. This may occur in two ways. First, by anion vacancy. A negative ion may missing their lattice side and leave a hole which occupied by an electron there by maintaining electrical balance. Second is by the presence of extra cation in the interstitial side. That is, it is extra cation, that is positive ion, is occupying the interstitial side. Dear friends, anions are negative ion and cations are positive ion, and electric neutrality is maintained by an electron is present in another interstitial site. Metal deficiency. This defect shows variable vacancy and occurs usually due to missing of a cation from its lattice site, and two monovalent cations is replaced one divalent cation to maintain electric neutrality. Third, impurity defects. These defects arise when foreign atoms are present at the lattice site in place of whole atoms or in the interstitial sites. Dear friends, now we are going to discuss doping. Doping is the process of adding impurities to a crystalline substance so as to change its properties is called doping. I repeat, the process of adding impurities to a crystalline substance so as to change its properties is called doping. Electrical properties of solid. First is conductors. The solids which have conductivity in the range of 10 to power 4 to 10 to power 7 per ohm per meter are called conductors. Second is insulators. The solids which have extremely low conductivity ranging between 10 to power minus 20 to 10 to power minus 10 per ohm per meter are called insulators. Semiconductors. The solids which have conductivity between the conductors and insulators ranging from 10 to power minus 6 to 10 to power 4 per ohm per meter are called semiconductors. Dear friends, now we are going to discuss band theory. So, in case of metals conductors, the atomic orbitals of the metal atoms are so close in energy that they overlap to form a large number of molecular orbitals very close in energy. This set of molecular orbitals is called a band. Two types of band formed when electron can easily flow by gaining energy and conduct electricity. If gap between band is large, electron cannot jump from valence band to conduction band. So these behave as insulators. If the gap is small, then electrons may jump and show some conductivity and act as semiconductor. Magnetic properties of solid. Diamagnetic substances. Substances which are weakly repelled by the external magnetic field are called diamagnetic substances. Example: TiO2, H2O, NaCl. Paramagnetic substances. Substances which are attracted by the external magnetic field are called paramagnetic substances. Example: O2, Cu2 plus, Fe3 plus. Ferromagnetic substances. Substances which show permanent magnetism even in the absence of magnetic field are called ferromagnetic substances. Example: FeNi. Antiferromagnetic substances. Substances which are expected to possess paramagnetism and ferromagnetism on the basis of magnetic moment of the domain, but actually they possess zero magnetic moment, are called antiferromagnetic substances. Example: MnO. Ferromagnetic substances. Substances which are expected to possess large magnetism on the basis of magnetic moment of the domain, but actually have small net magnetic moment, are called ferromagnetic substances. Dear friends, these are notes on solid state chemistry, and you listen this podcast on Sandhu podcast chemistry notes info. You can also get PDF notes of these podcast by visiting our Telegram channel. Link of Telegram channel you can get from the description of this podcast. Thank you to listening this podcast. This podcast is brought to you by chemistrynoteinfo.com.